Hi, welcome to the second lecture on Introduction to Computational Fluid Dynamics. I will be first explaining to you what is the use of CFD. Oftentimes as engineers, students fail to see the high-level picture of why CFD is used in industries, and hence we will spend some time explaining why computational fluid dynamics is seen as a solution for engineering problems. This is what we call as 50,000 feet view. So you are looking at a broader picture, and hopefully by the end of this lecture you will be able to recognize where computational fluid dynamics fits in the process of computer aided engineering. In this context, we will be looking at some applications. We will primarily focus on external aerodynamics, but I will also be giving other examples so that you will get a good sense of the different applications in which computational fluid dynamics is used. The other thing that some students lack a basic understanding of is how easy is it to set up a computational fluid dynamics simulation. Many students think that if they are able to follow up a tutorial in ANSYS Fluent and if they are able to set up a simulation, then that's it. This is good to get the initial motivation, but if you want to be serious about setting up a simulation and also make sure that you're getting accurate results, then you need to understand the fundamentals of CFD. And here what we will do is we'll take up an IC engine simulation. So here we will take IC engines as an example, and we will be looking at the different things that you need to take care of while setting up an IC engine simulation. Once we have shown that setting up a CFD simulation is a non-trivial process, we will then introduce what computational fluid dynamics is. And then we will look at the Navier-Stokes equations. And then I'll give you intuition behind numerical analysis. So first, let us try to understand the 50,000 feet view. So the first question that you need to try and answer is, what is the problem that engineers and scientists are trying to solve? And why is CFD analysis needed? And does CFD analysis actually help? So these are the fundamental questions that you need to ask as a curious learner of CFD. If you directly try to learn computational fluid dynamics without asking these questions, then you might have a limited understanding of the subject and you might fail to explore areas that you might actually be interested in. So in order to understand, or in order to give you this 50,000 feet view, let us take a simple example. So heavy duty trucks, that is our subject. And in the US, 70% of the oil consumption is used for transportation, and 20% of this is used by heavy duty trucks. So what is the problem here? Well, in 2016, the United States consumed 7.6 billion barrels of oil, and approximately 20% of this is being used by the heavy duty trucks. And the problem is 70% of this fuel consumption is to compensate for drag forces. If you're able to reduce the drag, it directly translates to fuel saving, which directly translates to profit for the companies that operate these trucks. Why is this an aerodynamic problem? Well, to answer that, let us take a look at the simple graph. Here on the x-axis, you're looking at level highway speed. So this is basically the speed at which the truck is traveling. And on the y-axis, we are plotting, or we are showing the horsepower consumption. So the highway speeds here in the US are typically around 70 miles per hour. You can think of that as an average value. When you go from 50 miles per hour to 70 miles per hour, you can see that the horsepower contribution almost increases by a factor of 2. And one of the reasons is because your drag coefficient is proportional to velocity square. And this is why engineers are so keen on reducing the drag coefficient. Okay, because even a marginal decrease in the drag coefficient is going to translate into great fuel savings. So once we have identified the problem, we should then spend time on understanding the problem. And for this, engineers come up with testing methods where they can systematically analyze the problem and then propose solutions. Popular testing methods include wind tunnel, CFD and road testing. So this is where CFD comes into the picture, and it is looked as a tool to test out different solutions. So let us take a look at the different testing methods and their advantages and disadvantages. If you take a look at wind tunnel, the process of testing a vehicle in a wind tunnel is relatively cheap, And the problem is accuracy and the amount of information that you can capture. Because at the end of the day, a truck is not going to be sitting in a wind tunnel, it's going to be traveling in a road where the conditions are not that regulated. And to do this, typically road tests are performed. But the problem with road tests is it tends to be very costly. We are looking at least $20,000 per test. Different countries have different regulations and hence different testing procedures have to be maintained. And this is why CFD is looked at as an ideal solution. One thing you need to remember is that CFD, at least at this point in time, is not 100% predictable. You always need to go back and check with experimental data to make sure that your results are accurate and you can actually trust them. And that is the disadvantage of CFD. The advantage is that it is very cheap, at least in a relative sense. But the disadvantage is that you cannot always do just a CFD simulation. We are at a point in time where we have gathered enough experience to know the drawbacks of certain CFD methods and models. And hence, with this experience, we are able to tell that, okay, you can trust, you can have a 70% confidence or 80% confidence in your CFD simulations. These confidence limits are established by companies and it completely depends on their testing procedure, and this data is usually proprietary. And that is why you don't see this data outside. So I hope at this point you see where computational fluid dynamics is being used. And as I mentioned a few seconds back, to establish confidence in CFD, what people do is they perform experiments and they validate. So here you're actually looking at a vehicle called as the generic conventional model. This is a model of a simplified truck that has been tested in a wind tunnel and has a lot of experimental data. And then whenever there is a new aerodynamic CFD code, they try to take this case, set it up in CFD, and then see if they're able to match well with the experimental data. This is called as the validation process. You need to do this validation process for different trucks, different configurations to make sure that you trust the CFD code. Just because CFD is giving colorful images doesn't mean that the results are always right. The process of validation is very important. And that is why a company, when it uses a CFD code, it takes a lot of time for them to change to a new code, because for each and every code, they have to repeat this process of testing and validation, which is very, very costly. And then once the engineers have validated a model, they are able to come up with solutions using computer-aided engineering. They try out different designs, they analyze different designs to see if there are any improvements. And then the results that look the most promising, what they do is they conduct experiments with it to make sure that the result is actually good. Now, the other thing as engineering students that you need to understand is that when a solution is proposed, it's not always perfect. Even engineers in larger companies follow the process of first proposing a design and then learning the outcomes and then slowly optimizing the design. Now here you can actually look at an evolution of the trailer designs over the past several years. The image on the bottom right corner is the newer arrow panels that you can see on trucks. But then, that was not the first iteration of the design. You can see that initially it started out quite different. Now, if you're from India, you would notice that there are still trucks in the road which are still flat faced and they have very poor aerodynamic performance. So I hope at this point you understand where computational fluid dynamics fits in the process of computer-aided engineering. Okay, that being said, CFD is used in a lot of different applications. So I'm showing some cool videos here. So the first video is from Total Sim. You're looking at a very cool volume rendering of an external arrow problem. And I hope at this point you understand why these type of simulations are required. With the CAD package, you can create several different iterations of the arrow panels and test them out very easily using CFD. The second example is an oil sloshing example. Trucks that carry a large amount of liquid, have this problem called as liquid sloshing. There's so much liquid that, when the vehicle brakes, then the inertia forces from this liquid can affect the driving performance. And CFD is used to estimate the forces so that better designs can be made to minimize the effect of sloshing on the vehicle dynamics. Computational fluid dynamics along with computational combustion is used to design the next generation hypersonic nozzles. With respect to hypersonic nozzles, the Mach number is so high that your air and fuel mixture do not have enough time to mix. Okay, and hence the combustion process can be highly unstable. With computational fluid dynamics, different nozzle designs can be performed, and then the residence time of the air-fuel mixture can be calculated or predicted. And then the whole goal of that study would be to optimize or to maximize the residence time of the air and fuel mixture so that they mix well and hence the combustion is much more stable. With advances in grid generation techniques and coupled simulations and increase in computing power, researchers are now able to simulate systems like the human heart, where they can try out different mechanical valves and look at the flow structures. Here CFD is very important because you cannot actually go and test these concepts in a real human being. Before it gets to the stage of clinical trials, computational tools are used to first make sure that there is some merit in these designs and there are no fundamental flaws. I hope at this point you have a very good understanding and appreciation for computational fluid dynamics. It is a tool that is helping engineers solve real-world problems. Now that being said, how difficult is it to set up a CFD problem? It is actually quite difficult. Though there are a lot of commercial softwares that make it seem easy, you need to have a lot of background and fundamental knowledge in order to be proficient with a computational fluid dynamics package. You first need to be a subject matter expert. For example, if you're simulating flow over a truck, you need to have the basic understanding of fluid dynamics. You need to know what drag coefficient is. You need to know what pressure coefficient is. You need to understand the concept of Reynolds numbers, skin friction coefficient, and so on. Without understanding these topics, if you are running CFD, then there's no point. Now, in addition to this, you need to have a good grasp of CFD concepts to take meaningful decisions and stay independent of a CFD code. And to kind of explain all of this, let me take a simple example. We are going to take a look at an internal combustion engine simulation and learn what it takes to actually set up one. Here I have this image from Wikipedia, which actually shows the processes that are involved in a 4-stroke engine. We might have studied this during our undergraduate thermodynamics course. It looks very simple. The concepts are fairly easy. But then what does it take to actually simulate something like this using CFD? So we start with geometry configuration. Here we create a clean CAD model and we split the model into meaningful domains. And then we need to calculate the fluid properties accurately. We need to define the mesh. When we define the mesh, we need to think about what type of meshing is ideal and where should the mesh be refined. We need to think about the governing equations, what equations to solve, which physical models to use, and we also need to think about the initial and boundary condition that needs to be applied. When we're talking about the geometry, you first need to create a watertight surface. Your surface or your geometry cannot have holes in it, it cannot have intersecting regions. If you have them, then the meshing process is not going to work. The second thing is you need to identify the intake, exhaust, and combustion chamber systems. When it comes to fluid properties, accurate properties needs to be calculated. And here, NASA polynomials are used to evaluate specific heats, enthalpies, and entropies, which are used in the governing equations. And similarly, if you're simulating fuel sprays, then you need to keep track of liquid properties like viscosity and thermal conductivity. And sometimes you need to make sure that you're taking into account of the real gas behavior and not using ideal gas approximations. Then we come to meshing part. In an IC engine, the meshing process can be very, very hard. And in addition to that, you also need to make important engineering decisions like what is the discretization length, how you're going to resolve the flow when the valves open and close, how small should your mesh be in order to resolve the flame front, and then what mesh resolution is required so that you can account for the wall heat transfer properly. So you can see that there are so many decisions that you need to make, and there are so many combinations or so many options that are available for you, and not all the options are right. And sometimes a particular combination of these options may be unideal and can lead to an unsuccessful simulation. If we are talking about governing equations, we all know that the basic conservation laws needs to be solved. But in an engine, the flow is turbulent. So in that case, you need to employ additional turbulence models like K epsilon, K omega SST, and so on. And if you have a fuel spray that is involved, you need to specify how the fuel is going to break up, how the fuel is going to vaporize and mix with the gas phase. And then you need to explain how this fuel and air mixture is going to combust. And then there's several combustion models that are available. You need to pick the right model. And then finally, you need to explain how emissions are going to be calculated from these simulations. You need to choose the appropriate models for it. I hope at this point you can understand and appreciate the amount of work it takes to set up an IC engine simulation. And I think it is also the right time now to define what is computational fluid dynamics. So as you all know, CFD stands for computational fluid dynamics. It's a technique that allows you to simulate fluid flow using a computer. Primarily, we solve equations called as the Navier-Stokes equations. We'll be taking a look at them. And then to get more information out of the simulations, you need to be solving additional equations. And this is typically the case when it comes to an engineering application. And sometimes the physical processes are modeled using simplified math equations for computational efficiency. Now let us say that you are interested in simulating the atomization process of a fluid flow. Typical fuel atomization spray simulations take about 100 to 150 million cells, and it usually takes a supercomputer to run these simulations. And that is why the atomization process is modeled using simplified equations. Now you need to remember that these models needs to interact with our fundamental governing equations. And then finally, numerical analysis is used to solve these governing equations on a computational mesh. And finally, engineering quantities can be obtained as outputs. Now, this entire process is what I would define as computational fluid dynamics. So now let us take a look at the Navier-Stokes equations. Historically, only the momentum equations was referred to as the Navier-Stokes equations. But these days, this definition is no longer used in a very strict sense. Many engineers refer to this entire set of equations as Navier-Stokes equations. Now, in order to use CFD effectively, you need to have a firm understanding of each of these terms. Okay, so we'll start with the dou by dou t terms. These are called as time derivative terms. They represent how the quantity inside the time derivative changes as a function of time. The next term is called as the convective term. You can see that the convective terms are spatial derivatives and they're pretty much present in all the equations. Then you have a pressure drop term. This term is responsible for capturing the effect of pressure. And then finally, you have your shear stress terms. These terms help in taking into account the wall effects. So one thing you need to remember is that irrespective of the problem that you're solving, you are always solving these equations at the end of the day, because these equations describe how the flow takes place without taking into account the application. So the way these equations are able to understand that the flow is actually taking place over an airfoil or the flow is actually taking place over a truck is from the boundary conditions. We will be talking about these more when we actually derive these equations. In order to have a firm understanding of concepts like discretization and boundary conditions, it is very important to understand the mathematical nature of these equations. You need to understand that these are a set of partial differential equations. They're coupled, they're non-linear, and they cannot be solved analytically. And this is the main reason for CFD. So what does that mean? For example, if I have a simple equation dy by dx is equal to e power x, then the solution to this ODE is y equal to e power x. And this is called as an analytical solution or an exact solution. So for the full Navier-Stokes equations, an analytical solution has not been derived yet. If you are unable to solve these equations analytically, then how do we solve these equations? We apply a concept called as numerical discretization. We will be explaining numerical discretization in a separate lecture. Numerical discretization refers to the concept of converting an ordinary differential equation or a partial differential equation into algebraic form by actually discretizing the domain in which they are getting solved. So a discrete domain means that you have a set of points and the function can be calculated only at those points. In between those 2 points, the best thing that you can do is interpolation. Okay. So here you can see that the blue curve is the original function. And then what I'm doing is I'm discretizing the domain by picking up 2 points, x and x plus h. And then what I can do is I can compute a derivative by calculating f of x plus h minus f of x by h. This is also what is called as fundamental theorem of calculus. And this expression is actually derived from the Taylor series. We will be learning about that as well. So one thing you need to remember is that the process of discretization is not that simple, right? Now to compute the same slope, what you can actually do is you can employ different expressions. You can use a forward difference technique, you can use a backward difference technique, or you can use a central difference technique. So you can see that each and every term can be discretized in a similar way, using the approach that we learned. But then what is next? I mean, if I write all of my equations in this way, what's going to happen? Well, you will end up with a system of equations. Okay. These system of equations form a matrix, and if you're able to solve the matrix, you will be able to compute the results for your x, y, and z components of velocity, the pressure, and temperature. To solve the system of equations, a linear solver is used. Now you need to remember that linear solvers is a separate area of study. People do their PhD in developing advanced solvers. But oftentimes people use simple solvers or rely upon third-party libraries. There are several advanced methods that are being used in modern CFD packages. We will be talking about them lightly in this class, but we won't be reviewing them in detail. But if this is something that you're interested in, you can always find these topics and then you can read about them more. So I hope this lecture gave you a very good understanding of the background and motivation to do CFD. And hopefully you got an overview of the steps that is involved in CFD. Thank you for watching. Bye.